So good morning also from my side. I'm Konstantinos Tserpes from University of Patras. And in the next, let's say 10 to 15 minutes, I will give you a short overview about the Morpho project. In fact, I will use a presentation given recently by the coordinator of the project at Le Bourget. The coordinator is Nazim Iqbal from ENSAM. So I would like to thank him for providing me, for allowing me to present you today what he presented recently. So Morpho, it's a European project. The full title is Embedded Life Cycle Management for Smart Multi-Material Structures with an application to engine components. So the project started in April 2021, and it will run for 4 years. So we are more or less in the middle of the project. The main challenge is to extend EU industrial leadership through cost-effective, flexible, and ecological manufacturing, maintenance, and recycling processes for the new generation of multifunctional airframe parts. So the purpose is to support the development of smart aerospace engine fan blades by endowing them with cognitive capabilities and optimize their manufacturing and life cycle management. So the consortium is comprised of 10 partners from 6 different European countries. The coordinator is ENSAM from France. In fact, ENSAM is participating with different entities, and PIM laboratory is one of the entities. Then we have TU Delft from the Netherlands, University of Patras from Greece, Safran from France, which is the end user of the project and the provider of the demonstrator, as you will see. Fraunhofer IFAM from Bremen, Germany, Synthesites, also a Greek company from Athens, Comet Group, a recycling company from Belgium, Phisens, a sensor provider company from Germany. Then we have the ESI Spain, which is a software company, and we have also Feuga from Spain, which has undertaken the communication activities of the project. So the goals of the project: to define, design, and validate an innovative, robust, and environmental friendly industrial process in order to manufacture, monitor during service, and afterwards recycle the new generation of smart, multifunctional, multi-material structures with a focus on engine fan blades, of course. We tend to rely on embedded sensors, different types of sensors, as you will see, data-driven hybrid twins, and machine learning algorithms to track the entire life cycle of the targeted aeronautical structure in real time. Finally, we tend to contribute to setting standards that will enable reliable, sustainable, agile, and cost-competitive industrialization of smart structures for aeronautics. So, our main demonstrator is proposed by Safran. It refers to an engine fan blade. This blade comes from the LEAP engine, and this blade is made of 3D woven CFRP material, and it is protected, its leading edge, it's protected by a metallic adhesively bonded layer, which can be made either from titanium or from steel, inox steel. You can see here a sketch of the fan blade. Of course, this fan blade, one of the dangers of the fan blade is bird strike. So we have in the project we have systematically investigated bird strike damage on the blade. From this blade, we have all let's say extracted a simplified structure, which is called FOD panel substructure. FOD stands for Foreign Object Damage Panel substructure, and most of the studies have been made for this FOD panel. So The specific objectives of Morpho are related to the different sections of, let's say, the life of the structure. For instance, objective 1 is related to digital industrialization and aims to develop online RTM process monitoring with a final objective to increase by 5 to 10% in the production. Objective 2 is related to the MRO, and it has to do with the health monitoring. And at the end, we aim to reduce of 50% the turnaround time. Next, objective 3 goes at the end, and it has to do with ecological and recycling. Under this objective, there is the disassembling of the FOD panel, and then the recover, recycling, and reuse of the carbon fibers. Objective number 4 is linked to the design phase. So for the damage-tolerant design of the FOD, instead of the safe life design approach, which is the current approach, and this will lead to more than 5% weight reduction of the FOD panel. So final objective 5, it relates to the use phase, and especially qualification standards and certification. And the aim here is to develop a roadmap for the adoption of standards for the ELCM. So in this slide, you can see the different technologies that are integrated in Morpho, and these technologies are spread in the different sectors or sections of the life of the structure. It starts, let's say, with a design which has to become a damage-tolerant design, and then it goes to the manufacturing process, then to the process of embedding sensors into the structure, then it goes to the disassembly and recycling, and then to the reuse. All these technologies are directed towards a digital, let's say, twin or a digital platform. In some cases, this is called hybrid twin, or because it is, let's say, calibrated or validated at the final stage using experimental data. So this digital platform will be fed with physical data, and then at the end we'll create, of course, digital data. And the main aim is to replace most of the experimental process and to reduce the cost and the time of the design of maintenance phase, of course, to, let's say, improve the techniques for recycling, use, and end of life. So to give you a cognitive paradigm for the manufacturing process of the panel, which is called RTM. We here added two different sensors, FPG sensors, fiber bracketings, and the electric sensors for process monitoring. And you can see here in this sketch on the right the process that has been followed. We have inserted sensors in preform layer. Then during let's say the manufacturing process, we have the cushion and resin injection processes. Afterwards, the resin is cured. Then go to the molding. Then we have after the manufacturing of FOD, the printing of the sensors on the surface, and on the front part, we have embedded fiber grade sensors in the FOD and sensors on the FOD in order to monitor on one hand the RTM process, and the other hand to be able afterwards to monitor integrity of panel by let's say monitoring things. In parallel, we've developed a numerical tool which has been used to numerically design this innovative manufacturing process, and at the end, this tool will be integrated into the overall digital twin that will be developed in Morpho. So some results using the sensors, we can let's monitor the RTM process as an infusion process. You can see here on the left how diagram we can, let's say, describe the stage. We can map the status of the resin infusion. We have a region with resin, a region with no resin, and than used, which is comprised of different sensors and different type of sensors. In this slide, you can see the network of the FBGs that have been inserted into the 3D preform before the resin infusion. On the right, you can see here the 3D preform. And in order to insert the FBGs, we have applied the manual optical fiber integration process, which uses, let's say, a steel capillary that it is initially inserted into the preform, and into the capillary the FBG are inserted, and afterwards the steel capillary is removed in order to leave the sensor into the preform. This process has been applied manually by Fraunhofer IFAM in Bremen, and you will see afterwards a video also of the process. So continuing, all these will be integrated at the end into a hybrid digital platform that will start from the manufacturing phase and will go until the final phases of the reuse and the recycling. In order, you can see here in this flowchart how this hybrid platform will operate. At the beginning, we tend to develop a data storage platform. Then we will have digital twin models for the RTM process, for the prediction of the damage, for the strain monitoring, and then for the disassembly process. These digital twin models will be fed with data, and then a data-driven online learning will be added. This will lead to hybrid twin models for the same processes, and then a model reduction scheme will be implemented, and at the end we will have, let's say, aircraft engine model of the smart fan blade that will be added with the product environment, and this will form the integrated digital platform, the interactive platform. So regarding the sensors, you can watch here a very short video. Okay, so this video describes shortly the main objectives in the manufacturing process for the printed sensors. You can see here on the right a small 3D woven CFRP specimen with printed sensors on it. Let's say the development stage is that the manufacturing process has been completed, and now we are at the phase of collecting the first results using these sensors. So regarding the SHM part of Morpho, this will be developed numerically, and at the end will have the form of a digital twin also. You can see here the development process. We have started with some virtual tests using multi-scale numerical models. In parallel, we have performed many mechanical tests using specimens at different scales, starting from coupons and going up to the FOD panel, as you can see here. These two, let's say, tools have been integrated. In the FOD, we have also used the sensors, and with the results of the sensors, we aim to develop a diagnostic module. And afterwards, by adding different tools to go at the end to a prognostic tool that will be delivered at the end of the project. The main process that, let's say, describes this SHM is a probabilistic SHM data-driven methodology to assess the damage and the remaining useful life of the FOD panel, and at the same time to consider ascended quantification, and this will be a process that will be validated in the frame of Morpho. So, regarding the disassembly and the recycling, which is, let's say, the task that it is mostly related to this small workshop, this is a task that is, let's say, developed within Work Package 6. The main partners for this task is ENSAM, University of Patras, and COMET. At the end of the life of the FOD panel, we will assess the material, and some University of Patras we will do this. And based on the outcome of the assessment, we will go to the reuse or repair phases, or we will go towards the recycling phase. And the first stage of this recycling phase is the disassembly. In fact, we want to disassemble the CFRP material from the metallic layer, and this needs to be done by, let's say, breaking the adhesive, by debonding the two parts. The main method used in Morpho is laser shock-based disassembly. This is an experimental process that is applied by PIM of ENSAM. University of Patras has also done simulations in order to virtual test and optimize the parameters of the method. After the laser shock disassembly, we will assess again the status of the CFRP material, and then the CFRP material will go to the recycling phase, and the basic recycling method that has been applied up to now by COMET is pyrolysis. And it is a very successful, as the first results have shown, process. In this slide, you can see the basic, let's say, the basic physics of the laser shock method. You have a high power laser source. It sends a laser beam, and then you have a confinement of the plasma on the surface of the coupon. And by confining the plasma, you generate a shock wave that propagates in the material. And also you have the main wave and the release waves. And by the interaction of the different waves, you are able to create stress fields at the different locations through the thickness of the specimen. And these stress fields are causing, let's say, interfacial fracture, which can be either a delamination or a debonding. By controlling the parameters of the laser process, you can place at different locations these stress fields, and you can, let's say, develop a customized disassembly process for the specific application. The objective, of course, is to break the adhesive and to separate the 3D woven specimen from the metallic protective layer. In this slide, you can see the first results from the pyrolysis recycling method applied on the 3D woven, the specimen on the left, and the fibers after the pyrolysis. Of course, the efficiency of the method has been evaluated by performing mechanical tests on the fibers, for instance, single fiber tension and single fiber pull-out tests, and also by assessing the remaining resin on the fibers. The results are very promising, and here in Patras, we will also apply solvolysis on the same material, and we tend to compare the results from two different fiber recycling recovering methods. So this from my side. Thank you.